Hi, my name is Alex Marder. I'm a research scientist at CAIDA, and I'm going to be talking about our work looking at cloud WANs. And these cloud WANs, at least for the very large public clouds like Amazon AWS, Microsoft Azure, and Google Cloud, which is the one I've got on the slide, they're really interesting. These are global networks that traverse oceans and have points of presence on every continent but Antarctica. We had three goals for this work that will help support the research we plan to do in the future. First, we wanted to find the cloud WAN interconnections for each of the three major public clouds, and we wanted to compare our results against some form of validation to improve our inferences. Second, cloud WANs allow you to set up virtual machines in different geographic regions, and the map on the right shows all of the different regions that we used to conduct our experiments. We wanted to figure out if clouds rely on Tier 1 and Tier 2 ISPs differently depending on where in the cloud the traffic originates. And when I say rely on, I mean handing off traffic to a Tier 1 or a Tier 2 network, either as a transit provider or a peer. Finally, we wanted to figure out where the clouds interconnect with each other, so we geolocated the interconnections that we found between the three major public cloud providers. Since everything we do relies on accurate cloud WAN interconnection inference, we first came up with an easy and repeatable way to validate our approach using Azure hostnames. Unlike AWS and Google Cloud, Azure router IP addresses have DNS hostnames, and Azure includes a tag in many of their interconnection hostnames containing the name of the neighboring network. In total, we found 214 unique tags embedded in the hostnames for 419 addresses, and we manually interpreted each tag. Obviously, this type of validation has a few limitations. Most importantly, we only validated interconnections for Azure, and it's less accurate and complete than validating with network operators at the cloud networks. However, it does have the advantage of being easier to reproduce when developing new techniques or checking analysis. And in the future, we plan to work with network operators at the clouds to validate our approach further. So now that we have a form of validation, we're ready to start experimenting. We set up virtual machines in all 32 Azure regions that were available to us. And each virtual machine sent a traceroute to every /24 covered by a prefix announced into BGP at a rate of 5,000 packets per second. All of this probing took about half a day. Then we used bdrmapIT to identify the network operator for each router observed in our traceroutes. When we compared bdrmapIT's network operator inferences to our validation set, they matched 87% of the time, and we realized many of the mistakes occurred for one reason. Our validation dataset contains Azure IP addresses on routers operated by neighboring networks, but we observed a lot of IP addresses from Azure's address space that followed our validation addresses. There's a few possible reasons why that could happen, but we're pretty sure that path changes in the cloud WAN corrupted some of the traceroute paths. Our theory is that sending traceroutes in the conventional way increases the chances of path change corruptions. In our experiment, we use Scamper, which is a wonderful tool that uses conventional traceroute probing. It sends probe 1, waits for the reply, then sends probe 2. This means that the only way to achieve our 5,000 packet per second rate is to parallelize across traceroute destinations, leaving lots of traceroutes in flight at any given time. If the WAN changes paths, it could potentially corrupt any of the traceroutes currently in flight. Our solution was to change the way we probed so that we sent probes without waiting for replies, leaving only one traceroute in flight at a time. Overall, our fix improved bdrmapIT's router operator accuracy from 87% to 97%. And after the change in traceroute probing, we no longer saw any Azure IP addresses following an address in our validation dataset. Alright, so that was the first goal. And the second goal was to see how cloud reliance on Tier 1 and Tier 2 networks changed depending on the source region. And this is especially interesting for Azure and Google Cloud, who use cold potato routing, where they try to hand off packets as close to the destination as possible. To do this, we set up virtual machines in every region of AWS, Azure, and Google Cloud, and each virtual machine conducted a traceroute to every /24. And then we ran bdrmapIT to infer the router operators and cloud WAN interconnections with neighboring networks. Next, we computed what we called the cloud transit degree for each cloud neighbor network. The cloud transit degree is essentially a count of how many networks the cloud reaches through a specific neighbor. So in the example, the cloud reaches 4 networks through AS1, giving it a degree of 4. And while the cloud only hands off traffic to AS5 when the destination is in AS5. So it has a cloud transit degree of 1. And we computed this metric separately for each region, so essentially we computed it separately for each virtual machine. On the right is a summary of what we observed, and the paper goes into more detail. Basically, we found that clouds use tier 1s and tier 2s at different rates depending on the source region, indicating that the next hop network depends at least in part on where traffic originates. And the graph also shows that the clouds still rely heavily on ISPs to reach most internet networks. But we didn't try to determine if specific ISPs were transit providers or peers of the cloud networks. Okay, so that was the second goal. And the last thing we tried to do is to geolocate the interconnections between the cloud networks. Our basic strategy was to use IXPs as landmarks. Each cloud appears to peer extensively at IXPs, and we know where these IXPs are since that information is listed in PeeringDB and IXPDB. When a cloud interconnection IP address shares a common predecessor in our traceroutes with an IXP address, we infer that the interconnection occurs in the same city as the IXP. This is because we expect that the common predecessor is likely on a router co-located at the IXP. And here I've plotted all of the interconnections we could geolocate. The takeaway here is that the clouds appear to interconnect with each other all over the world, and often all 3 clouds will interconnect with each other in the same cities. I should note that while we could geolocate all of the interconnections between AWS and Azure, and between Azure and Google Cloud, we could only geolocate 34% of the interconnections between AWS and Google Cloud. Most of those interconnection addresses did not share a common successor with an IXP. So to wrap up, we were able to improve bdrmapIT's inferences for the cloud WAN interconnections from 87% accuracy to 97% accuracy, mostly due to just changing the way we sent traceroute probes. We also found that the clouds use tier 1 and tier 2 ISPs at different rates depending on where the probes originate. And finally, geolocating the cloud WAN interconnections showed that the clouds interconnect with each other in cities all over the world. All right, so thanks for listening, and I'm happy to take any questions.